Hello, my name is Leon Liu. I will be presenting our research on our proposed diagnostic model that combines image segmentation models and CNN classifiers to provide explainability in digital pathology, particularly for lung disease diagnosis using chest X-rays. In AI-driven diagnosis using medical imaging, deep neural networks are often applied as convolutional neural networks architectures that are effective at diagnosing with accuracy. However, they provide little insight and transparency in the final result, and it is difficult to trust or interpret their decisions. To improve upon this, our technique uses UNets and class activation mapping. UNets are image-to-image models that produce segmentation masks as results instead of just a predicted classification, as is the case with CNNs. On top of this, class activation mapping, or CAM, creates localization maps by extracting the weights and features of a CNN classifier, revealing which areas of an image most heavily contribute to a model's diagnosis. Grad-CAM is a form of CAM which uses the gradients of the class scores with respect to the feature maps instead of the weights themselves. Our proposed pipeline aims to use a transfer learning CNN model and a UNet model to produce a final visualization that combines the Grad-CAM heat map extracted from a CNN with a lung segmentation produced by a UNet overlaid onto the original chest X-ray to create the final visualization. This is a diagram of our transfer learning model. The second box here represents any of the backbone models that we have tested, such as Exception or ResNet. Rather than flattening out the feature maps from these convolutional layers in the transfer model and passing them into one-dimensional hidden layers, as often seen in fully connected CNNs, the output of these convolutional layers are instead then connected to a global average pooling layer and then straight to the softmax layer. This gap layer better preserves the relationships between the final feature maps that Grad-CAM creates the heat map from and the output, as there are less weights there are pretty much no weights in between, which would not be the case if there were more hidden dense layers that have weights in between. And we choose to extract the last convolutional layers feature maps because they generally have the most semantic grasp of these disease regions and are most closely related to the final output, whereas earlier layers tend to capture more general elementary patterns such as maybe edges. Here's a diagram where the previous transfer learning model is used to produce both the classification and the Grad-CAM heat map. And here's the diagram of a UNet model. It is a modified autoencoder model with skip connections shown by these gray arrows from one encoding block to decoding blocks, which I'll get into, that preserve details that are potentially lost otherwise when encoding to smaller dimensions, the finer details, in a traditional autoencoder. We have symmetric encoding and decoding blocks that contain convolutional layers represented by these blue arrows, and deconvolutional layers that encode and decode respectively. Between them, max pooling, these red arrows, and upconvolution, these green arrows, half or double the dimensions from one block to the next. Our two hyperparameters are the number of encoding and symmetric decoding blocks, these larger chunks at each vertical level, as well as the number of filters. The small number above indicates the number of filters per convolutional layer, which gets doubled in half per block. The number of filters determines how many feature maps we end up after going through a convolutional layer. Our training loss function is categorical cross entropy. We also evaluate the results with dice loss, which compares the intersection and union of the predicted mask with radiologist labeled ground truths for the UNet image segmentation. And here's a sample feature, which is a lung chest X-ray and the corresponding ground truth label. These lungs are healthy, but the dataset also contains cloudier X-rays, which we'll see later on, for the diseased lung images. And it is important to train the UNet on both so that it's capable of segmenting both healthy and unhealthy lungs. The datasets for classes are normal, healthy, COVID, pneumonia, and then general lung opacity representing other diseases that lead to opacity in the lungs. Here's the train test split. For the UNet model, 1,800 images are used to train the model, and the classifier trains on 10,000. And here we have the sample UNet results from some testing data for our best model, which is UNet 5E16F. 5E is 5 encoding layers and 5 decoding layers. 16F is 16 filters. Our tested parameters are 3 through 5 for E and 16 through 64, or 16, 32, 64 for filters. And we found that lower filters but higher number of encoding blocks generally perform better. The second and second to last row, labeled pred, are the predicted masks and the predicted mask overlaid onto the original chest X-ray. The first and last row are the ground truth radiologist labeled masks. What we can see is that in column 6, which has the most cloudiest image, and also slightly in column 2, is that our mask error are greatest for these more diseased lung images, whereas the model tends to perform better on clearer images, which makes sense as the edges are less clear when there's more cloudiness. Our final dice loss over all our testing images is 0.0309. And then next we have our transfer model results. Our best transfer model is exception with 95% accuracy on testing data. And here are some of the final visualizations that combine the UNet lung mask from our best model with the Grad-CAM heat map taken from various transfer learning models, labeled here on the left. Every 4 in the top left, top right, bottom left, bottom right is a different model. And each column corresponds to the Grad-CAM map for that class alongside the confidence that the model provides. We can see that for exception, it is the most discriminative with nothing in the other columns except for COVID, which is the true predicted class. And it has the second highest confidence out of all of these. These visualizations provide another lens through which we can analyze medical images and judge an AI's results based on its ability to discriminate and identify the correct regions. By reversing the image segmentation maps, we can also detect the AI's model's attention on unwanted areas, like outside of the lungs. And a doctor can offer a second opinion by analyzing the disease areas that the model predicts and see if these are accurate. We believe that this proposed pipeline may be applied to other medical imaging techniques, such as brain scans, and provide more interpretable AI-driven digital pathology. Thank you.